Hey everybody. Uh, there's something that we've been talking about all semester long that we've kind of been dancing around and we haven't talked about in some real depth, and that's energy. And so I'd like to give a little bit of treatment of that so that when we talk about it for the rest of the semester, which we're going to be doing, we have some understanding of what we're saying. And energy can be a little tricky, because energy is kind of abstract. And so one of the reasons why understanding what is energy is such a challenge is because it comes in many forms, and so we're not always talking about one thing when we say energy. And yet it's essential to understanding why anything works in physics, in the universe. Because what is energy? In general, energy is anything that causes change, anything that does work in the universe, anything that makes things go. And so when we're talking about the energy of a system or the energy that an object is emitting, that can mean a lot of things, or the energy can come from different places, but the one unifying thing that they all have in common is that energy makes things work. Energy causes change in any system. And so one of the reasons why energy can be so challenging is because energy does come in many different forms. So, for instance, what kind of energy could we be talking about? Well, there's what's called kinetic energy. Kinetic energy is the energy that an object has based on its motion. Energy is how much, kinetic energy is how much energy an object has based on how fast it's moving. If an object is moving, it's moving because it has kinetic energy. The faster it's moving, the more energy it must have. Thermal energy is the energy of heat, the energy that something has based on its temperature. If an object is hotter, what are the atoms doing? They're moving faster, right? The hotter an object is, the higher the average speed of the atoms and molecules in the object. So thermal energy is another expression of kinetic energy. The thermal energy of an object, the heat energy that an object contains, depends on the total amount of kinetic energy of all the atoms and molecules in the object. So thermal energy and kinetic energy are both energies that give objects speed or movement. Radiative energy is something we've already talked about. Radiative energy is the energy that's carried by light, by photons. How much energy is being carried by the oscillating electromagnetic waves of those photons, of that light. Then there's potential energy. And potential energy is a little hard to wrap your head around, because potential energy is energy that is stored up in an object. So you don't really see potential energy because it hasn't been released yet, right? The reason why it's called potential energy is because this energy has the potential to be turned into some other kind of energy, to be turned into something that will do work, that will show change. So that's what potential energy is. It's potential because it still has the potential to do something useful, but it hasn't done that yet. And so it is still stored up in the object. And there's a couple of main kinds of potential energy that we're familiar with in everyday life. There's gravitational potential energy, which is the energy that is stored in an object based on its position in a gravitational field. So if I lift up a rock off the ground, or this book, right? If I lift up this book, that doesn't happen spontaneously, right? Things don't just start floating up in the air on their own. It takes work. I have to use some energy. My arm has to use some energy to lift up this book against the gravitational field, the gravitational pull of the Earth, which naturally wants things to fall down. So I have to use up energy. I have to store up energy. By lifting up the book, I am storing gravitational potential energy into this book such that if I let the book go, it doesn't just sit there, it falls. The book starts moving. By releasing the book, by lifting up the book and then releasing it, I have taken the gravitational potential energy that I've stored in the book and I have turned it into kinetic energy. The book starts moving. This is how a hydroelectric dam works, right? You dam up a river, the water level rises, and as the water level of the lake behind the dam rises, the gravitational potential energy at the top of the lake gets higher and higher and higher and higher against the downward pull of Earth's gravity. And then when you let the lake pour over the dam, that water starts to fall faster, 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 faster. The gravitational potential energy that you've stored up in the water, as it falls faster and faster and faster, that gravitational energy turns into kinetic energy, and it moves. The water falls faster and faster until that water hits a turbine, and that causes the turbine to spin, and that spinning turbine turns into electricity. So by damming up that river, you've taken this water, you have stored gravitational potential energy into the water, and then when you release the water down the dam, the gravitational energy turns into kinetic energy, and then when that fast-moving, fast-falling water hits a turbine, it spins the turbine and turns that kinetic energy into electrical energy. Chemical potential energy is kind of similar. Chemical potential energy is the energy that is stored up in the molecular bonds of molecules. And so this is how we power our bodies or power your car, right? Molecular bonds store up this chemical potential energy, and so when you eat sugar or fat or molecules that store up a lot of energy, you eat the sugar, your body digests the sugar and breaks those chemical bonds, releases the chemical potential energy and turns it into heat, or turns it into energy to power your body, right? So when your body burns sugar and it lets you run down the street, or it keeps your body warm. The chemical potential energy is turned into kinetic energy if you're running down the street, or it's turned into thermal energy to keep your body warm. Right? Oops. So think about this. Right? If you throw a ball up into the air, does the ball have the most kinetic energy right as you release it, as it's going up in the air, as it reaches the top of its arc, or as it starts to come down? What do you think? Well, what happens? As you throw a ball up into the air, it moves slower and slower and slower. It's moving the slowest here, and then as it starts to fall, it starts to speed up. So when will the ball have the most kinetic energy? When it's moving the fastest. When is the ball moving the fastest? Right as it's leaving your hand. Because right as it's leaving your hand, it hasn't started to slow down yet. So it'll have the most kinetic energy at point A. When will the ball have the least kinetic energy? Kinetic energy is the energy of motion, so it'll have the least kinetic energy when the ball's moving the slowest. So when is the ball moving the slowest? Right as it's reaching the top of its arc. It's going slow, slow, slow. It's moving slowest here, and then it starts to fall and it starts speeding up again. So the ball has the least amount of kinetic energy at C and the most kinetic energy at A. So as it goes from A to B to C, it's slowing down. It's losing kinetic energy? Where's the kinetic energy going? How is it losing kinetic energy as it goes up, 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 up? Well, the ball is getting higher and higher and higher off the ground. It's getting farther and farther from the center of the Earth. So as it gets higher and higher in the sky, the ball gains gravitational potential energy. So where is this kinetic energy going? Why does the ball go slower and slower and slower? Because that kinetic energy is turning into gravitational potential energy. This is an example of the number one law of physics. The most important law in all of physics is the law of conservation of energy. What does that mean? It means that energy is conserved. If something is conserved, what that means is nothing is lost. So when I say that energy is conserved, what that means is the total amount of energy of a system stays constant. The total energy stays fixed. So that as you throw the ball into the air, yeah, you're losing kinetic energy, but energy can't just disappear. The energy has to go somewhere. And so in this case, as you throw this ball up and up and up into the air, it's going slower and slower and slower. It's losing kinetic energy, but it's gaining an equal amount of gravitational potential energy. Let me say that again. As the ball loses kinetic energy, it gains an equal amount of gravitational potential energy, so that the total energy of the system, the kinetic energy plus the potential energy, stays constant. Right? This is what we mean when we say that energy is conserved. That the total energy of the system, the kinetic energy plus the potential energy plus the thermal energy plus all the kinds of energy, the total energy stays constant. Energy never springs up out of nowhere. Energy never disappears nowhere. The total energy stays constant. Energy can change forms. Energy can switch from one type into another. Energy can be transferred from one object to another, but the total energy of the system has to stay constant. This is going to be true of every system everywhere in the universe. So whenever we're talking about energy and objects gaining energy or losing energy, if energy is being gained from somewhere, it has to come from somewhere. Energy doesn't just show up out of nowhere. And if an object loses energy, like when a star loses energy out to space, how is it losing that energy? Energy doesn't just disappear from the universe. That energy has to go somewhere. In what form? Well, when a star loses energy, it loses energy by giving off light. So the total energy of every system has to stay fixed, has to stay constant. That energy has to be conserved. Keep that in mind throughout the rest of the semester. The last thing to talk about with energy is temperature. We've all semester long, we've been talking about temperature of objects. We just talked about how you can measure the temperature of a star using its spectrum, and pretty much every time we've talked about temperature this semester, we've measured it in Kelvin. Let's unpack that for a second, because we're going to talk about wide ranges of temperature throughout this semester. For example, from the hottest planet to the coldest planet, or planetoid, whatever you want to call Pluto these days, we go from very hot. Venus's surface temperature is about 750 Kelvin, which is very hot by planet standards, because Earth's temperature is only about 290 or 300 Kelvin. Once you get out into the outer solar system, the planets get cooler and cooler and cooler until you get to Neptune or Pluto, where the temperatures are only like 40 or 60 Kelvin, which is very cold. But if you don't know what these numbers mean, if you don't know what these temperatures, what these numbers in Kelvin mean, then I'm just throwing out numbers and it doesn't mean anything. So let's unpack, what are we talking about when we're talking about temperature in Kelvin? Because, if you grew up in the US, you're probably most familiar with the Fahrenheit scale, right? The Fahrenheit temperature scale is based on 2 fixed points. Water freezes at 32 Fahrenheit and it boils at 212 Fahrenheit. And every other temperature in Fahrenheit is relative to those 2 fixed points. If you've taken a chemistry class recently, or if you've spent a lot of time outside the US, then you're probably also familiar with the Celsius temperature scale. And the Celsius scale is pretty similar, right? The Celsius scale is based on 2 fixed points. Water freezes at 0 Celsius and it boils at 100 Celsius. In astronomy, we tend to measure temperature in Kelvin, because in astronomy, what if there's no water around? What if you're talking about the temperature of a star? There's no water inside of a star. So telling me the temperature of a star in Fahrenheit or Celsius doesn't really mean much, because I don't care what the water is doing, or I don't care what the temperature is relative to what water does if there's no water. So the reason why we prefer to talk about temperature in Kelvin is because the Kelvin scale is entirely based on energy. The Kelvin scale is based entirely on how much thermal energy the object has. If an object has no thermal energy, if the thermal energy is 0, the temperature is 0 Kelvin. 0 Kelvin is the lowest possible temperature in the universe. That's why 0 Kelvin is called absolute zero, because if your object is at a temperature of 0, it has 0 energy. And you can't have less energy than no energy. So the nice thing about the Kelvin scale is there's no negative temperatures. 0 is the lowest possible temperature because it is the lowest possible amount of energy that you can have. 0. There's no maximum temperature. If you keep adding energy into a system, the temperature will just go up and up and up and up. Which is nice, because here in astronomy we're going to deal with some pretty cold objects, like planets in the outer solar system, where the temperature is only a few dozen Kelvin, to inner planets like the Earth, where the temperature is about 300 Kelvin. And keep this in mind when we talk about temperatures of planets. Room temperature here on Earth is about 300 Kelvin. So that makes a nice round number to stick in your head. Once you start talking about the temperatures of stars, the surface of the sun is about 5,800 Kelvin. But that's the surface of the sun. And as you go deeper and deeper and deeper inside the sun, the temperature actually gets hotter and hotter and hotter, so that the temperature of the sun, the surface of the sun, may only be 5,800 Kelvin. But when you get down to the core of the sun, it gets up to 15 million Kelvin. And that's just the temperatures around our solar system, from the core of the sun out to the outer solar system. So we're going to go through some pretty wide ranges of temperature. And this is important because what that means is you go through very different amounts of energy. The great thing about the Kelvin scale is that the temperature is just directly proportional to the energy. If you double the temperature, you double the amount of thermal energy. You triple the temperature, the object has tripled the amount of thermal energy. There's a direct relationship. You don't need to do any multiplying by 5/9 or adding or subtracting 32 or whatever you have to do to convert from Fahrenheit into Celsius. If you have the temperature of an object in Kelvin, you just have a direct knowledge of how much energy the object has. And that makes keeping track of how much energy does it have? How hot is it? What do these numbers mean? It helps keep everything straight, because they're just directly proportional to each other. So that makes life easier. We're going to talk about this over and over again for the rest of the semester, so I wanted to give you this quick treatment of energy and temperature so that when we talk about it in an application in astronomy, you're not seeing it for the first time. So, thanks everybody.